Hello and welcome to this lecture where you are going to learn more important concepts about neural networks. The first one is the bias unit, as you can read here. You can see in this image the structure of a neural network, which has the input layer, the hidden layer, and the output layer. There are weights connecting the neurons. The bias unit adds an additional neuron to each of the layers, as you can see here and here. For example, these weights in bold that flows from the bias to the hidden layer and from the bias to the output layer. When we apply the sum function, the bias is considered in the calculations, and they aren't connected to any previous layer. Bias is just like an intercept added in a linear equation, an additional parameter in the neural network which is used to adjust the outputs along with the weighted sum of the inputs to the neuron. The bias value allows you to shift the activation function to either right or left. Most neural network libraries already include this unit by default, so you don't need to worry about that. We can see some definitions, different values even if all intries are 0. For example, if all inputs are 0, when you add a bias unit, the result of the mathematical operations won't be 0, so it will change the output. Another concept is the error calculation, and you learned the simplest equation, which only subtracts the expected outputs by the neural network predictions, as you can see in this table. However, there are more efficient ways to calculate the error when training a neural network. The mean squared error, MSE, and root mean squared error, RMSE. When a number is squared, the result is never negative. Let's take a look at the mean square error equation and the same table we had before, the class or the expected outputs and the prediction. We can see the application of the formula fi minus yi squared. So we just subtract the values the same we did before, but the difference, the subtraction is squared. We can see the results here. The sum of all the values is 1.011. This part of the formula, the mathematical symbol, and then to get the MSE, we just divide by the total number of rows, which is 4 in this example. So, mean squared error equals 0.252. RMSE is similar. You can see the equation here. The only difference is that you extract the square roots of the MSE. So we can see the result, which is equal to 0.501. The reason for using these metrics is that the numbers are squared, which indicates that larger errors will have a greater impact than smaller errors. In other words, this calculation penalizes bigger errors. For example, let's suppose that the error is only 2. Number 2 squared is 4. 2 times 2. And let's suppose that the error is 10. 10 squares equals 100. 10 multiplied by 10. So we can conclude when the error is 2, there is a small error, only 4. and when the error is 10, there is a big error because when you square 10, the result is 100, and there is a big difference between 4 and 100. In short, big errors will have a greater impact. Let's move on to another concept. We can see this other table, credit history, debts, properties, and income. Based on this personal data of the clients of a bank, the goal is to predict the risk to give a loan to the clients. For example, regarding the credit history, there are some values 1, 2, and 3. 1 could be a good history, 2 a median history, and 3 a bad credit history. Debt means if the client has any open debt with the bank. 1 equals yes, 2 equals no. Properties means if the client has cars or houses. 1 yes, 2 no, and the annual income. For example, number 1 could be annual income less than $15,000, 2 between $15,000 and $35,000, and 3 greater than $35,000. And the risk can be low, medium, and high. And the goal is to send this personal data to the neural network in order to get a prediction if the bank will give or not the loan to the client. See that this data is in a different format. Instead of 1, 2, and 3, there are these other formats which is related to an encoded version of the class. For example, low risk equals 100. This is the encoded version of this kind of risk. The encoded version of medium risk is 0, 1, and 0. And finally, the encoded version of high risk is 001. And we use this data format when there are more than 2 classes that we want to predict. In last lectures, we were dealing with the logical operators. There was just one neuron in the output layer because there were only 2 classes, 0 and 1. When you are dealing with problems with more than 2 classes, as in this case, we will have the total amount of neurons in the output layer of the neural network equals to the number of the classes. In this scenario, there are 3 classes, so there would be 3 neurons in the output layer of the neural network, and they will represent it this way. If the risk is low, we expect higher values in the first neuron and lower values in the other neurons. When the risk is median, we expect higher values in the second neuron and lower values in the first and the last neuron. And finally, when the risk is high, we expect lower values in the first 2 neurons and higher values in the last neuron. This is the representation you need to use when you have problems with more than 2 classes. There are basically 2 types of gradient descent. The first one is the most classic and is called batch gradient descent. We select all the instances, as you can see here, and send them to the neural network. The algorithm will calculate the error for all rows and then update the weights. In other words, the adjustment of the weights is performed at the end, after calculating the error for all instances. We can see in this image the input layer, which corresponds to these attributes, and the output layer composed of 3 neurons, as I said before. The batch gradient descent calculates the error for all rows and updates the weights, the same I said just now. The other type of gradient descent works as follows. We select an instance, as you can see here, calculate the error and update the weights. Then, we select the other row, we calculate the error and update the weights. Select another row, calculate the error and update the weights. This is the stochastic gradient descent. Calculates the error for each row and updates the weights. It is faster because it is not needed to load all the data into memory. For example, if there are 1 million instances, it will not be necessary to load all instances at the same time, as it will be loaded one instance at a time. We can see some more definitions regarding the stochastic gradient descent. It helps prevent the local minima to find a local minimum instead of finding the global minimum, and it is faster. No need to load all rows into memory. There is another type of gradient descent which is the most used, which is called mini-batch gradient descent, and it is a combination of batch gradient descent and stochastic gradient descent. The developer can define the number of instances, so we can choose a number of rows to calculate the error and update the weights. For example, if you choose 10 instances, the algorithm calculates the error for those 10 instances and then updates the weights. After that, more 10 instances are sent to the neural network. It will calculate the error and updates the weights. It will be done 10 by 10. Most libraries for neural networks have a parameter called batch size, so you can easily set this value. And as I said before, it is the most used and it presents good results. Let's move on to more concepts regarding the activation functions. You have learned the step function. It is the simplest and it returns only 0 or 1. You can use this function for simple problems. Then we can see the sigmoid function, where the values are in the range from 0 to 1. This function is used when you have problems with 2 categories or 2 classes, because it will return a value from 0 to 1, like a probability. If you need to return negative numbers, you can use the hyperbolic tangent function. Here you can see the equation, and if you want to check the result of value 50, you need to replace x in the equation by 50. So you will know in which part of the graph that the value will be placed. The maximum value is 1 according to this upper line, and the minimum value is -1 according to the bottom line. We can see that this blue line touches all the points on the graph, which is why we can say that it returns values in the range from -1 and 1. Another activation function is the ReLU. It is one of the most used, especially in the hidden layers of the neural networks. It is the rectified linear units. The equation is quite simple. it will return the max value, and if you send a negative number, 0 will be returned. For example, if you send 10, the result will be 10. If you send 15, the result will be 15. On the other hand, if you send -4, the result will be 0. -15, the result will be also 0. You can see this straight line, so it will return values greater or equal to 0. There is no maximum value. There is another very important function, which is the softmax. You can see the equation here, and it is quite similar to the sigmoid. However, the sigmoid function is mainly used in the output layer when you have problems with two classes. When you are dealing with problems with more than two classes, you need to use the softmax function, since it will return probabilities for each one of the classes. For example, when you send some data to the neural network, it will return a probability regarding each one of the classes. Going back to that example of giving a loan to a client, the neural network will return a probability low for risk median and for risk high. As you can see here in this example, the probabilities of green, blue, purple, reds, and so on. This is one of the most used activation functions, as I said before, in the output layer of the neural network. And finally, there is the linear activation function. As you can see here, it returns negative and positive numbers, and there is no lower or upper boundaries. It is used in regression problems, when you want, instead of classifying the instances, you want to get a value. You send some data and you will have a number as a result. For example, based on the expenses on the credit card, the algorithm will predict the new limits to the client. It will return a number. That's all for this lecture, where you have learned some more interesting and important concepts about neural networks. See you next time!